All right, welcome to another exciting day of software estimation and measurement. We're going to continue on today with estimating effort and build off of what we talked about last time. I do want to point out some things coming up next week. Not surprisingly, a paper due on Tuesday. And then there is the midterm project, which is due on Thursday. Any questions about the midterm project? Have you read over this?
Yeah.
So in general, it's collect 3 complexity metrics, and I've listed some options there. I've listed your options there, and do it for 3 pieces of software. They can be software you wrote. They could I analyze it against BlueJ, for example. Have you used BlueJ in another class? Maybe it is a IDE, an integrated development environment. So I thought that'd be kind of interesting. You would expect them to have good coding practices. I don't know, but what is the complexity for that and others? And then put it in a report. I don't want a long report. I'm thinking 1 page is where it should be. Use graphs, and then literally copy and paste this onto the second page of the report and fill in the values. Okay, that's 2 points. Okay, just to copy and paste that. That's so that you know that, oh, Dr. Carroll really wanted me to use graphs or charts. Well, let me just go back and change that, and then let me update the rubric. Nobody has to know, and then submit it. Okay. So, and then it also helps point out, did you do 3 programs? Did you actually report the metrics, etc.
Do the programs have to be a specific length? Because as the...
No, in fact, I'd like you to do a variety. Okay, so I mean, one of them could be your own student project. Okay, something you wrote, something you're very proud of, or something you don't mind sharing with me. I need to be able to have a URL or a copy of the program. Okay, so that's the only really restrictions. GitHub has thousands of them. Okay, the class is I think in the syllabus, I mean in the course catalog, I think it does specify Java. There are other languages you might consider using. I'm fine if you do that, but I felt officially we should do Java. Let me know if you have any questions on that. Okay, that is coming up, and that is worth a midterm grade. Okay. All right. And then spring break is in 2 weeks. We will not hold class for the online section or the face-to-face section. So there's that. Okay. So what did we talk about last time? What is effort again?
The estimated number of staff months, the time and the number of people required.
The estimated number of staff months, that's correct. And it's usually estimated instead of in the past. Usually, once we've estimated, we try and hold to it. We spend a lot less effort looking in the past to say what was it in hindsight, because the project's already done. So we need to be careful what is included in metric. We should expect surprises. There's different categories for using methodologies and models. We talked about several of these. Expert opinion, benchmark data, analogy, proxy points is where we left off. Today we're going to cover proxy points, custom models, and algorithmic models. What did you think of the Delphi or wideband Delphi method? Do you remember what they were? They were methods of which to come to a consensus by using anonymous estimates, and then with the wideband Delphi model, discuss them with the moderator. So if the three of you were the experts in the company and you had all estimated the effort or schedule or some other aspect, then you would submit yours independently, and then if I were to moderate, you could ask, one of these is twice as big, what do we think about that the interface should take an entire month or an entire year? And you have to be careful not to give away your estimate by saying, well, I felt like, but to be able to do that, to be able to see the other estimates and then say, in my gut, I knew that was a little low. But this is for expert opinion as a way to come to consensus. You might consider this maybe with a hard decision. Please submit 3 proposals and don't put your names on them. You might collect those 3 people in a room and say, here's the 3 proposals. Let's talk about them, and then I want you to go back and resubmit your proposals. And then maybe you could reach consensus by iterating on that. Interesting method. There's some transferable skills. Benchmarks data is great if you have it, because it's in the past instead of an estimate. So, and along those lines is analogy. So benchmark data is like you're just assuming it's exactly the same. Analogy respects that there are differences, and we come up with modifiers to approach that, to say, how do we adjust that? Now, we started talking about proxy, where proxy is a noun. In my dictionary, it says a figure that can be used to represent the value of something in a calculation. So it's standing in place of something else. And so we use these proxy points to be able to get at them. They're proxies for sizes. Okay? And I outlined last time 3 of them: function points, which we've talked a lot about, object points, and then use case points. So let's talk about each of these methods today. Oh, I already did that. Okay. So in general, each of these have 3 steps. Step 1 is to estimate the size, and hopefully you recognize this is a motif in the class, a recurring pattern where we have that size is so important. It's the basis of so many things. So we have the lines of code, function points, or some other proxy point metric. Step 2 is then to adjust the size estimate for complexity. This should sound familiar with what we talked about last time, or difficulty. It's, hey, we recognize that there are differences and that we need to account for them, and so we're going to adjust them accordingly and be able to scale them to be able to get a better effort estimate. And then and some things to consider are what about security? Is this high security demands? What about algorithmic complexity of it? Is it very complex? Are there strong performance metrics we need to meet, especially like in the terms of communication? So are we going to be doing a lot of transferring of communications? So we need to know that those are reliably going through. What sort of warranty are we putting with this software? And these are just an example of other things to consider to adjust. Okay, so we've estimated the size. We've decided, okay, well, let's adjust the size and then apply the productivity factor. Okay, so what is our productivity factor? And to be able to scale it. So there's two ways to do this. We could do it manually, where if we're doing it manually, this is just simply divide the adjusted size by lines of code per staff month, or function points per staff month. If we're using a tool, then we can account for size, environment, our development process, and other factors as well that are more complex to be able to account for. Okay, so these are the three general steps with proxy point: size, adjust the size, and then apply the productivity. Let me spell correctly. Productivity factor. Okay, so let's get into these one by one. So function points. Okay. By the way, do you have an opinion about function points versus lines of code? Like, yeah, you can see why they came after, they're better, or I'm just going to count lines of code, I can't imagine that being better, or I don't know, I'd have to test it out to see. I want to know if you're forming an opinion. Okay. Something to think about. Do you feel like one is going to be better? Do you feel like, hey, if I'm estimating large projects, I'd want to be function point certified because I think that has a lot of merit, or I'm just going to count lines of code? Okay, just curious. With function points, we need a way to convert function points to effort and duration, a schedule, things like that. Okay, so we have function points. We say, okay, this is how many functions. This is our function point count for this project. Now, what are we going to do? So we got lots of options. Let's discuss these in turn. Okay, we could just use the function point count. Okay, and to do this, we could use it. We could compare it. Pair it with benchmark data. Now that would presume that we have benchmark data and that the project is similar and that we can come up with that and make it match up. Or we could use a tool, for example Kokomo, to be able to calculate the effort. That's option number one. Using the function point count. Option number two is, maybe surprisingly, maybe not, take the function points and convert them to lines of code. Okay. Now we can, there's a pattern here. We can either compare it again to benchmark data using lines of code, now that we've converted it, or we can use that as input to something like Kokomo. Okay, number three is engineering rules. We're going to spend more effort on this because the other ones are building off of what we've already talked about. So engineering rules are best practices approach to what's going on based on experience. So project duration, we use a floating point count raised to some power d is the variable. Okay, and you're like, okay, well, what's d then? So here's a little table of different values of d. It kind of depends. So if it's an average project, welcome.
Excuse me, is this a computer lab?
It is not a computer lab. Are you looking for a computer lab? There is one down the hall. There's one down at like 450 or 451 that's open.
Sure.
Okay. There is 5 computers out, but 4 of them are laptops. We should delete that from the video. Okay. I didn't even look up before I said welcome. I just assumed. He's like, I'm not entering this class. Okay. So on an average project, like, I don't know, I don't have an experience, I'm just getting started with this. So if you don't know, it doesn't fit one of the other project types, then raise it to the 4/10 power. Okay? So that'll scale it down. So just in case you don't think in exponents, so 0.5 would then be the square root. So this is smaller than the square root is what we're doing here. So, but maybe it's a simple project. So then we would raise it to the 0.32 power. If you're dealing with a military project with its restrictions, qualifications, overhead, etc., and 0.45, so that's suggesting it's going to take a longer time frame than the average project. Okay. If you're dealing with web projects, we break them up into two categories. A large web project is scaled at the same amount as a simple project, but a small web project has a longer duration. Does that make sense? Why would we do large web projects have a smaller exponent than the small web projects? So something to keep in mind here is that, okay, so a large web project, this value is going to be higher. Okay? And so imagine you have, what's a good analogy? You're asked to produce something. You're asked to make something. We'll do food. I like to cook food. So if I were going to make a chicken cordon bleu, which is very time intensive, you got to wrap everyone, versus I need to crank out 6 large pizzas. That's like an average for my family. We just do them and then freeze half of it. So while the project for the pizzas is larger, the time per serving is smaller than the chicken cordon bleu fancy dinner with some asparagus and some parsley and some other garnish. You know, that per serving is going to have a higher cost per serving in terms of my time to make that. Hopefully you've all had a good breakfast before we had class. I'm hungry already. I've already eaten twice. Do you see how that works? So economies of scale, you have a large project. Well, yes, it's larger, but because it's larger, we can divide it up. We can, okay, well, these 3 parts are very similar, so we can do one and then reuse a lot of it to do the other one, reuse a lot of it to the third one, so then you're getting a large project done with less work per unit. And so that's just some intuition on small web is going to have a longer duration, but it's also a smaller project. So it's going to be shorter, a lot shorter because it's a smaller project, but it's going to take more effort per unit because it's smaller. Okay? So instead, you know, if you had 1 screen for a small web project and you have 10 screens for a large web project, well, that first screen is going to take the most time probably, the second less time, third less time, fourth less time, etc. Okay, so that's some intuition behind that between the large web and small web. Okay, so that's duration, and I'll spell check it before I post it. By the way, these notes are available. They are not live right now, but they will be once I sync up. They're in estimating effort, effort.text. No, they're not. Estimating effort. Uh-oh. Sure thought they were. Oh, they will be. They will be. Okay. My apologies. They will be there once I transfer them. Okay, so these notes are online in case you want to review them later. Okay, so that's duration, engineering rule for duration. Let's talk about engineering rule for staffing. So these are good to just have at your quick disposal to do. Back of the envelope, okay, what are we looking at? Now, I'm not very good with raising something to the 0.32, but that's okay. I can just quickly take a calculator and be able to do that. 0.32, and there we go. If we had 100 function points raised to the 0.32 power, that would suggest that we're talking about 4.36 staff months. Okay, or months. Sorry, that was months. Okay, so duration is months. So if we're talking about staffing, though, what we do is the engineering rule is take the function point count, divide it by 150 to get staff months. Okay, and if you're doing, and that's for a normal project. If you're doing a large maintenance project, then the number is scales much better in terms of a fewer staff count. You can divide it by 750 if you're just maintaining it. Okay, so you can see there, what is that, for 5 times you need 1/5 the staff for doing a maintenance project versus doing a development project. Okay, so then that's an easy back of the envelope. Okay, how many staff months should this project take? Okay, so then now that we have duration and we have staffing, then we can come up with effort. As you've probably guessed, effort is staffing times duration, and so then we get our effort, and this is measured in staff months. Okay, so we have a staff count times the total number of staff months, and so we have our effort there. Now here's another interesting engineering rule to apply, and that's requirements creep. What does creep mean? At least in this context. Creep means something that's slowly moving, slowly changing. If you're creeping out of the room, I'd expect you to be like slowly walking, like so slowly that nobody noticed, type of a just very slowly but moving. Okay, so that's what creep means in English. So this just amazes me. It's 1 to 5% per month. 1 to 5% per month. And you might say, well, that's really small, Dr. Carroll. What's the big deal? Okay. So, good to know is if you don't know what your customer or your management is, just use 2% for an average. Okay, so Albert Einstein has been attributed. Sorry. So what's the total feature creep is another way to say it. Requirements creep, feature creep for a project that will take 2 years. How do we calculate that? The project's going to take 2 years. So if we used a compounding formula, Albert Einstein has said, it's been attributed to him, that's in debate, that the most powerful force in the universe is compounding. So that's probably that is a formula you should know. You can use it to calculate interest on a loan or the gain on an investment. Anybody know the formula? Okay, so we're having transferable skill day today again. So compounding formula is you take 1 plus the rate raised to the time. Now, this is the simplified formula. Often you take the rate divided by the number of periods and then times by the number of periods, like if you're compounding monthly. But this simplified version will work for today. So here, what does rate mean? Rate is the rate of increase. So here this would be 2%. By 2%, that equals 0.02. If you use 2, it'll be 200, and things get crazy quickly. N here is the number of periods. How many periods are we talking about? So here we're talking about compounding monthly, so that means there's 24 periods. So then now we have 1 plus 0.02 raised to the 24th. And it's 1.61 is what we get. It's 1.61 approximately. So that equals 61% if we're compounding. If a feature has the compounding effect on the feature. Now, if you're just taking it and multiplying it by the 24 months, then that would still be 48%. So it depends on if you believe that you have compounding feature creep. If, hey, you know that early feature? Well, you've done such a good job with developing that, we want it to change it again. So 48% or 61%, that's huge. How would you like the midterm changing, 61% from now till when it's due? You'd say that's ridiculous. That would show up in the teacher evaluations. It may even affect re-enrolling. So luckily in academic settings, usually the requirements are fixed, they're well thought out because the project's been completed before, and so you don't have this requirement creep. But in the real world, it's, I don't know what I want you to build it, it's never been built before. Oh, now that you started building it, now I know more what I want, and now I realize I need these things. Okay? Something to keep in mind. Okay, we've got an exercise. So applying these things. Okay, so function point engineering rules. So let's assume that you have a new 275 function point count web project that you're going to do for UITS. So let's use these engineering rules to get a quick estimation to determine the duration, staffing, effort, and requirements creep. Okay. So let's do this. Let's pull this up on the screen. I know a better idea. Let's make this, change the width. Okay, I'm gonna pause the recording while we work on this. I'm gonna float around. Okay, I'm sorry. There we go. That's what we're looking for. Okay. It is one thing to see it, it's another thing to do it. So let's, I think every one of the students in the face-to-face class just came up with a different answer. That's okay. Okay, so how do we calculate duration? 275 raised to the Okay, so that's the question then. What is the project type?
I consider it as a small web project.
All right, good. We have 3 opinions. That's what I like. We have small web, we have average, and we have simple.
Large.
Sorry. Simple or large web. I couldn't tell from your numbers. Okay, I'm going to go with small web. Okay. So if we went with small web, 16.6, well, we can't really have, we don't want to report 16.6 staff months. I think we'd better just estimate, let's just assume 17 staff months to round it out, make it a little easier. Okay, now what's our staffing needs here? Divided by, is it 150 or 750?
150.
It's going to be 150, so what does that equal?
I think 1.83.
Okay, I need 1.83 of you to leave the room.
2.
How do we do that? Okay, so we're going to say, 2, because you can't hire 1.83. Now, you can hire like 1.5 in terms of, or 6.5. You could say, your half of your time is assigned to this, but you can't get real fine. And so I would be leery of doing anything finer than a half time. So two people. Okay, and notice we have these numbers that we turn out, and I think a lot in academics it's, what's the answer? It's 1.83 repeated. No, that's not the answer. It's 2. Because we're dealing with discrete human beings here. And we can't have somebody working on it for 0.83% of their day and 17% on another project. Okay, so now we have, it's going to take 17 staff months. So how does, so what do we do?
150 into duration.
We take what?
Staff 17 into 2. Yeah,
17 times 2 equals 34 staff months. Okay, so notice duration and effort are both staff months. What's the difference?
I think duration is just months.
It's what?
Just
Duration
months.
must be just months instead of staff.
It's just months.
Yeah.
That would make it easier to explain. So this is how long it's going to take your staff to complete that. So if we drop months, I think that'd be a little cleaner to how to describe it. This is how many.
Because the effort is staff into duration, and if the units of duration is staff months, the units of effort must be staff square months.
Okay, so we have duration is months. Staff is count of people. And people don't like to be divided up. Effort is staff months. And then the unit for requirements creep is a percentage, okay? Okay, so what's our requirements creep? So I want you to think about those. So do your numbers make sense? What one of you, in terms of your effort and your duration, are they the same order of magnitude? Are they, do they make sense? So requirements creep, how are we going to calculate this? Do we know for UITS, do we have an idea of what their requirements creep is? Are they really good? They know ahead of time exactly what they want, or they change their mind often? We don't know, right? It's just a hypothetical situation. So we're going to use 2%. So if we have 2%, then we for a lower bound, we could say, hey, we're going for 17 months, so that equals 34%. For a higher bound, we could say, well, it's going to compound. So we're going to raise it to there's going to be 17 months of which we're going to get increased feature creep. And that equals what? 1.41. Well, 1.41 equals 41%. So, and this was not meant to be a negative, this was meant to be a range too. So it depends if you're just going off a strictly linear or if you're compounding it. So, but you could expect 34 to 41% increase in recall. That's huge. That's huge. Okay. Questions on these? All right. So that was function points. Remember, we're in the category of proxy points here. And another one we said was object points, okay? So object points. Okay, so this is especially applicable for 4GLs. What are 4GLs? They're fourth generation programming languages. What's a fourth generation programming language? Well, what's the first one? Low level machine language. So ones and zeros. Second generation, by the way, this is how I learned how to program. My engineering introduction to computers class, for the first week or two, we did ones and zeros. I'm like, oh, I'm programming a computer. This is so cool. And then the next week we moved to assembly, which is a second generation language. I thought, whoa, this is way better than programming with ones and zeros. Okay, there's a lot more sense of what's going on here. And then after doing assembly for a while, we added a high-level language. We added C to it, which is a third generation language, 3GL. And then I thought, oh, okay, wow, now we're cooking with fire here. Now we're moving. This is great. So then a fourth GL would be like SQL, a database scripts, things like that. And there's even 5GL, fifth generation. What would that be? Visual programming like Visual Basic, or we've seen recent development of programming languages geared towards teaching younger people like Scratch and things like that. Okay, so this is especially applicable for fourth generation ones. Okay, and what it does is it measures screens, reports, and your 3GL modules that you need to introduce into it. So those are the inputs for it. And okay, so that's objective points. Let's talk about use case sizing. That was more than I wanted. Okay, so this is a popular method for capturing and specifying functional requirements. It came after function points. If you want to see more information about this, you could see uml.org, okay, for more information about use case sizing. And it's like function point counting, but starts with use cases and actors. Okay, well, what does that mean? So actors are users or external systems. So what goes into it, okay? And use cases is what types are we going to use this as? And there's an 11-step process for doing use cases. I'm going to summarize these steps here instead of explicitly go through them all. Anybody do their own taxes in the U.S.? U.S. taxes? The 11 steps felt like taxes. Fill this number out, fill this number out, take these two numbers, combine them. Now fill this number out, now fill this number out, now scale it, now take the 4 numbers together, and then you have your answer. Okay, so the 11 steps summarized are calculate the product, so multiply the of use cases and actors. Okay, so do we have an administrator and a user? How many external systems are we hooking up to it? How many different types of users are we having? And then multiply that by, well, okay, we have this use case and this use case. And then what we're going to do is we're going to adjust this value by our technical and environmental factors. So this should start to feel like, oh, okay, I feel like we're doing the same thing over and over again. We take a value, we tweak it by adjusting it by to scale it higher or lower depending on the circumstances, and then from that we calculate the effort and schedule. Okay, and so that's how use case sizing works. Questions on that? Okay, let's talk about custom models now. So you might feel like, you know, these are good, I have my preference on estimating size, but I've been doing this for 10 years, I feel like I've got a good grasp on it, so you could feel free to derive your own estimation model that is tailored for your environment or organization. Okay, so what kind of projects do you work on? What do you do? Well, and there's some steps on how to approach this in a disciplined manner. So 4 steps. First is, if you're making up your own model or calculating your own model, that sounds a little better, determine the major factors. Okay, and so what are the major factors? So let's have an example here. Let's say we're talking about a mobile app company. Okay, you've been producing mobile apps for 10 years. You're an early adopter. So what sort of things would you, if you were, anybody done mobile app development? Okay, well then, so let's just stretch ourselves a little bit. What would be the major factors if somebody said, hey, I want an app, and you were a developer and you were trying to understand how much effort, what would you ask them? If you're trying to get at the primary factors. I would, now we're not going to use this as, you know, definitive, but just as a brainstorming exercise, you might say, okay, well, how many different screens, how many different views are you going to have, okay? Because every new screen has its all intricacies in designing it and getting it right. How many connections to the server? How many times, you know, is it going to be going back and forth? Is it bidirectional? Is it how's that going to work? Because that's can change your complexity greatly. Or maybe you feel like, depending on the type of apps you do, is this just a menu option? You know, are we just, each menu option is going to come with a different thing? So if this is what you felt like, oh, you tell me you have a new project, and I can just, with these 3 primary factors, I can estimate it within, you know, 80%, for example. Now this is just a few, maybe you have 10, and then you run through, okay, somebody is asking for an estimate to build a mobile app, and it has these characteristics. Okay? So step 2 then, once you've identified the major factors, what do you feel like has the most impact on your effort? Then it's determine the cost of the major factors. Okay? So again, let's go back to our mobile app company that we're going to start up after class. And so we might say, okay, adding a new screen that has a value of X, adding a new connection to the server, or you could spell that out, you know, is it a bilateral? You could a bidirectional, sorry, connection with the server, or are we just pulling from the server? And maybe adding a new menu option. You say, well, that has cost Z. Okay, well, that's great. You just pulled these numbers out of a hat. Or, you know, your own expert opinion. But so now that's great, but let's verify this. So let's collect some data. So now you can either gather, maybe you have the data on this all ready to go, or you could pull it out of reports quickly, or so gather or start collecting, depending on the statistics based on your primary factors. Okay, so let's gather data and see, okay, well, if we use these three simple primary factors, are they going to be able to tell us? And so then we want to correlate using regression the data. Okay, so I said these are the primary factors. Do we have data on how long these projects took? If we do, then how close are we? And what you might want to do is propose 3 models and see how well each of them correlate with the data. Now you might say, wow, this method correlates very well with half of our projects, but not the other one. Okay, well, maybe that was your small one. Maybe that was your first job for a new client. Maybe it was the, you know, 3rd or 4th job with the client. And so maybe that model fits really well there. But you need to correlate with the data to see, okay, well, you know, we just came up with this. How well does it work? Okay? So, I mean, don't expect all the models to fit your company, your situation perfectly. They give a good basis and they give a good framework for, okay, this is a good way to approach a model. Okay. All right, let's talk about algorithmic models, okay? As you've probably guessed, these typically use size, and when you think of size, you think lines of code or function point count, and then process some characteristics to produce an estimate of effort, schedule, and cost. Okay, these are empirically derived, so they look at data and they get their results empirically derived using regression analysis. Okay, so we have 2 approaches. We have manual and we have tool-based approaches. As you could guess, the manual ones are much simpler and the tools are much more complex. For example, they might take into account a Monte Carlo simulations. They might do 1,000 Monte Carlo simulations to say, hey, with this probability, then we feel like it's going to work. Now, this might sound great, but they do have some limitations. So these are approximations. Okay, so studies have found that 50% of the time they're greater than or equal to 25% off. Okay, and that's even after calibrating calibration. So let's first talk about the manual models first because they're simpler. Okay, so we have these manual models, and the manual models all fit the same formula of A plus B times size raised to the C. Okay, and as you would guess, A, B, and C are empirically derived constants. Okay, so there's several models that exist. If you're like me, I like to see it rather than have to calculate it. Okay, so I took these models, the Walston Felix, the Boheme Simple, the Bailey Basili, and Dottie, and these are the values that they have for them. Now notice, not all of them have a value for A. So only the Bailey Basili has a value for A here. The rest have values for B and C, and they don't differ that much. Except notice, I mean, there's some real interesting differences here. The Walton Felix says, okay, our exponent is lower than 1. Okay, let's get some intuition from this. Okay, so as our I'm sorry. I copied and pasted that. Sorry, this should say 1,000 lines of code. I copied and pasted it here because I thought I was being fancy. Now I'm not being so fancy. I'll replace this graphic. Sorry. So the Walton Felix model is 5.2 times thousands of lines of code raised to the 0.91. So that means as our code size increases, and so this graph, notice, the x-axis and the y-axis are both logarithmic, so you need to account for that. Okay. As the 1,000 lines of code increases, they're saying, okay, that it's easier to deal with larger projects. The larger projects, we can deal with them better. The overhead, even with the overhead of larger projects, that we can, the effort is lower. So this says that the lower the effort per function for 1,000 lines of code, the effort actually decreases per 1,000 lines of code as it gets larger. Now other models, and so that is our Blue Diamond here. Okay, so Blue Diamond has a slight inflection where the others are increasing the other way. Most noticeably the one with the largest exponent here. It increases, and so you can see this general trend. Now this is getting to be very large projects here. So these are 1,000 lines of code. So then 1,000 lines of code. So this is 1,000,000 lines of code. Okay. So I don't know that these models were really meant to do 10 million lines of code, but I wanted to show you, 1,000 lines of code to 10,000 lines of code. Notice how they are different. Now this might bother you. It's like, whoa, wait, I'm used to there's one answer. There's not one answer. These are estimates. So it depends which model was calibrated, empirically derived, fitting your project most closely. So maybe you're saying, oh yes, so my projects look a lot like the projects that were used to come up with this model. Okay, well then you'd expect yours to be a lot closer to this. Or maybe you feel like it's a lot closer to the Bailey Basili model. But they differ, okay? And so notice those differences. And then also notice that, so the Bailey Basili, so if there is a constant factor A, what does A mean? What's the intuition for a constant factor? A plus B times C. So A is going to be just, okay, what's the overhead? What does a project take no matter what size? You still have to submit your report. You still have to make an invoice. You still have to do these things. And so that's kind of where A comes in. Okay, so that's some intuition behind the A, B, and C. Now, as you can tell, I also created these for function point. Okay, and so for function point here, we have function point on the x-axis, and this is correct and this is correct. And then we have effort on the y-axis again. Now the x-axis and y-axis again are logarithmic, so you got to keep your thought in that. You know, it makes a big difference if your student project is 10 times larger, so just keep that in mind. But notice what some of these projects, these disagree even more so in my opinion. Notice, for example, the Cremier one has this small factor here, but then it says, hey, it grows, and it grows huge as the function point count goes up. We're cubing it, but it has a small amount here. So then this is saying, hey, it doesn't really matter if it's 1,000 or 10,000 lines of code, or sorry, if it's going to be 1, 10, 100, or almost even 1,000 function points. That those are small projects, and it's going to take you know, some background effort just to knock this project out and get it done. But as they get bigger, the effort starts increasing rapidly. Okay, and so I thought this one was interesting, and so this one is going to increase much higher than the other two, but otherwise it's in between the two. Okay. Now we've just got a couple more minutes, so let's now talk about a tool in particular, and that's the constructive cost model. This is abbreviated Kokomo. Okay. This is probably the most popular algorithmic model and most influential. So this is from Barry Mohim. And so in the 1970s, that was a little while ago, we had Kokomo 1 or Kokomo 81. He published a book, 81, talking about Kokomo, so it depends on how you reference it. So, and then in 1995, 1996, Kokomo 2 came out that was an improvement. So Kokomo 1 is based off of 63 projects at TWR Aerospace. So in the 1970s, he was a senior engineer at, I don't know, that wasn't his title, but he was in charge of a division at an aerospace company, and he had 63 projects that ranged from 2,000 lines of code to 100,000 lines of code. Okay, so this Kokomo 1 is very characteristic of if you're developing aerospace code. Kokomo 2 is based off of only 161 projects. Now that's a lot of projects, but again, does it fit for your web development or other situations? Okay, and so for Kokomo, there's 3 classes of projects. We have organic, we have semi-detached, and we have embedded. Okay, so what do you mean by organic? So these are simple projects with known environments, and we're generally talking about small and experienced teams. Okay, so these are a lot easier to do well. So semi-detached is the term given to them for medium-sized projects with medium complexity. Now embedded has a tight and inflexible environments, so we're just going to say complex environments. Okay, so to capture that, you could think military applications would often be embedded. Okay, so now Kokomo estimates effort, and so I updated this graph to add in. So Kokomo doesn't have a constant, doesn't have an A. Oh man, it's all FP. That's going to bother me. I'm going to replace those 2 graphics. My apologies. So this should be 1,000 lines of code. Okay, and notice they don't differ very much between the organic, the semi-detached, and embedded. And here's those three plotted on the same graph as these other models. Okay, so where are they? Organic is this blue one here. Okay, so it's right in the middle of those maybe. Semi-detached is a little harder. It's more at the upper range there and growing. And then embedded grows a lot more and distinguishes itself, but it's not too far off from these other models. Okay, so you should at least be somewhere in between all these models. And it's not quite the same knit, but it's almost embedded is on one side and Bailey Bacilli is on another. But it partly depends. Are you more at this range, and or are you talking about huge projects? Okay, and so that's effort, and so they just apply these constants. And my apologies on the graphic. I'll update that. Now we can also update duration. Okay, so months, and we do so for each of the three classes, just like we have effort for each of these three classes. So organic is 2.5 times our effort raised to 0.038. And interestingly enough, the constant for each one of these is the same, and the exponent changes just slightly. Okay, so that's saying in how long is the project going to take is scaled by the effort, but there's this inherent constant 2.5. Okay, so now we have another exercise. No, we don't. We are out of time. Okay, in my last minute, let me summarize. There's an exercise on there. That there are different software estimation tools depending on different factors. Internal factors, external factors, environment, the customer, the language. You can combine these estimates, and so you should. And when you're combining estimates, remember what the engineering rule was. You should choose three. Now, don't just choose any three. You should choose three that are different. So if one's top down, make sure another one is bottom up. If one is expert opinion, use one that's analogy. Don't just do expert opinion 3 times. That's not really 3 methods. So if you have expert opinion, do proxy points. If you're doing expert opinion, make sure you're getting experts with different experience, or you really only have an expert opinion instead of expert's opinion. If you're doing proxy points, also have one with analogy. Now be careful, Kokomo is so popular and influential to make sure that you're not using 2 derivative works of it, that they aren't both based off of it. And then lastly here, let's talk about aggregating estimates. So you got some options. You could pick your favorite. Okay, that I mentioned that because that's done in practice sometimes, so we should acknowledge that. We could look at the mean, or we could do a weighted mean, where a weighted mean is if you had 3 values, you could do 1 times the smallest plus 1 times the largest, plus 4 times the mean. Okay, if you had 3 values, and then you need to normalize it by 6. So then that gives some weighting to the smallest, some weighting to the largest, but they're probably outliers. And so there's a weighted mean. Or you could do, you could scale each estimate by your own confidence scaler. If you've been doing this for a while, you might say, yeah, we've had a lot of success using use cases or something, and then make sure all your scalars sum up to 1. Okay, that's what we have for today. We'll see you next week.